Hi and welcome back. We're going to be discussing power series, but specifically we're going to be discussing finding the radius of convergence of a power series, not what the power series represents. We'll do that later. Okay. Okay. So the example we're going to have is this series, okay, and is going to be the summation from n equals 1 to infinity of minus 1 to the n multiplied by x to the n over n. Okay? And we're going to determine its radius convergence, etc. Okay? So the test that I'm going to use is I'm going to use the ratio test. You could use the root test, but I just enjoy the ratio test better. Okay, so I'm going to identify the a sub n. Because I take absolute values, I'm going to drop the minus 1 to the n. There's just one extra thing to write down, but you could if you wanted to. Okay, and so the ratio test is going to tell us to compute this. Okay, we're going to do our trick to simplify this and invert and multiply. So I'm going to have x to the n plus 1 over n plus 1 multiplied by n over x to the n. Now I get to cancel some things, and I'm left with this limit as n goes to infinity of the absolute value of x times by n over n plus 1. Now we could either use calculus 1 or L'Hopital's rule from calculus 2 to compute this limit, and we see that the limit of n over n plus 1 is 1. So it converges to absolute value of x, and that's what the limit is. Okay. So let's write down the statement of the ratio test. So by the ratio test, the series, well, 1, it converges if the limit is less than 1. 2, it diverges if the limit is bigger than 1, so absolute value of x bigger than 1. Okay, so this looks like a lot like the statement that we had last time, okay, in the opening introduction video. And 3, no info if absolute value of x equals 1, i.e. x equals 1 or x equals minus 1. Okay, and in this no info case, try another test. And we're going to do exactly that. So right now, it's very, very similar to our opening example. Diverges for bigger than 1, converges for less than 1. But let's investigate what happens if x equals 1. If x equals 1, I need to go back to my original series. Here it is. Okay. And when I plug it in, I'm going to get this. The summation from n, let me check where it starts, n equals 1 to infinity of minus 1 to the n multiplied by 1 to the n divided by n. Okay, great. Awesome. Well, this simplifies to be the sum from n equals 1 because 1 to any power is just 1. I get to forget that second term in the numerator. And I'm just left with this. I claim that this converges. And the test that I'm going to use is the alternating series test. Because I'm looking at this and I'm saying, hey, that's alternating. Okay, so when when we get the no info part, we need to select another test. I could have selected any test, but here, because it's alternating, and we've practiced selecting tests for specific series, the alternating part stood out, so I'm going to use the alternating series test. So alternating series test, the first thing that I'm going to check is that, hey, I'm going to call this b sub n. I'm going to call that the positive part. And that seems to be bigger than or equal to if I was to plug in n plus 1, because the denominator here is bigger. So it is decreasing. Okay. 2, this limit as n goes to infinity of b sub n is equal to this limit as n goes to infinity of 1 over n, and that's 0. So by the alternating series test, this summation from n equals 1 to infinity of minus 1 to the n over n factorial is convergent. Okay, and that corresponds to when x equals 1. So here it converges when x is 1. Okay, so I'm going to put a check mark next to x equals 1 to say, yeah, it converges. Now let's try x equals minus 1. Okay, well, the series that I'm going to get is the sum from n equals 1 to infinity of minus 1 to the n multiplied by minus 1 to the n divided by n. And, using properties of exponents, I can combine those two. This is going to be minus 1 to the 2n. And 2n, that's going to make every term, every exponent is going to be even. So if n equals 1, I get 2, n equals 2, I get 4, n equals 3, I get 6. So every single term is positive. So this is the sum from n equals 1 to infinity of 1 over n. This series right here, we need to test it for convergence or divergence. And there's two tests I could use. I could use the integral test, or I could recognize this as a p-series with p equals to 1. Because it's a p-series with p equals to 1, hey, this tells me it's divergent. Or I could use the integral test. Either way, we know it's divergent. So it's divergent, and I'm going to put an x here. Okay. So in summary, we know this. The series converges if x is between 1 minus 1 and plus 1. We know at x equals 1, hey, it converges, so I'm going to put that less than or equal to. When x is minus 1, we have that x there. It doesn't work. So its radius of convergence is like this, or this. Either one. That is the interval of convergence. The radius of convergence, if I was to draw this, here's going to be minus 1, here's going to be 0, and here's going to be plus 1. I'm going to see, hey, it works at 1, so I'm going to fill that in. And it converges all the way up to here. It diverges when x equals 1, so we usually put an open circle. I'm also putting the corresponding brackets. Then, when x is bigger than 1 in absolute value, that's a no-go. Like, that'd be here. Don't go in the red zone. Okay. But we do go, we have a yes here. Then we'll put the no and the no. Okay. So we have its interval convergence. We see, hey, I can go a radius of 1 in this direction. That's r equals 1. Or I can go a radius of 1 in this direction. So there is a radius convergence that's 1 in this instance. Okay, and the key takeaway is if you're asked for the interval convergence, I've written it down 3 times. Any one of these is sufficient. Okay, thank you very much.